So hello everyone again. This is lecture 1 part 2 of Semiconductor Electronics Materials Devices and Simple Circuits. In the previous lecture we just started the concepts of vacuum tubes in the introduction part only. Let's move on with the further discussions on that topic, and then we can go on to further concepts such as P and N junction, transistors, etc. in the subsequent points. Okay, so let's have a discussion. I am Samir Lavankar. Let's begin our discussion. Okay, so right now we are on the introduction part only. Let us first understand the introduction and then we can move on to classification of metals, conductors and semiconductors. So introduction, these all things have already been explained very clearly in the previous part of this lecture. So right now in the last lecture we completed this till this point. Let us understand from the next line here. Okay, so note that the supply and flow of charge carriers in the semiconductor devices are within the solid itself. So basically the passage is in the solid itself. This is what they are trying to say. While in the earlier vacuum tubes or valves, the mobile electrons were obtained from a heated cathode and they were made to flow in an evacuated space or vacuum. So what does this line try to make you understand is, in the previous era of vacuum tubes, the current or the, let's say, electrons were were present here, then it tries to move outside, or let us say the electrons are moving in this complete portion. But what is happening in these ICs? In ICs the passage is only and only inside this complete circuits. So this is one of the advantages of using these circuits. This is explained in this lecture. This has been explained in this point. Okay. No external heating or large evacuated space is required for the semiconductor devices. Quite evident, this doesn't require any external heating, not even large evacuated space are required. You may have seen these integrated circuits on the motherboard directly being placed. So it doesn't require any large evacuated space. Very less amount of height. These ICs also have very less amount of height, and hence it is very compact to put even in circuits. Okay, so no external heating or large evacuated space is required by the semiconductor devices. They are small in size, quite evident. Everything you may have seen the resistors also in current electricity or even in labs. So they are very small in size, consume low power. They consume very low power, operate at low voltages. So this is one of the differences. As you can see that the vacuum tubes were operating at high voltages, but these devices are operating at low voltages and have a long life and high reliability. So this is one of the advantages. I will just write it here again. So it is having long life and it is having high reliability. So please remember this, that these are the basic differences between vacuum tubes and normal our day-to-day solid state semiconductor devices. Okay, so what was it? So basically these were operating and having limited life and low reliability, but today's semiconductor electronics have long life and high reliability, and hence this can be used in your subsequent applications. So that was the complete conclusion of this lecture slide. Let's move on to the next slide now. Okay. So even the cathode ray tubes used in television and computer monitors, which work on the principle of vacuum tubes, are being replaced by LCDs with supporting solid state electronics. So in the previous era, around 20 to 25 years back, around 20 years back, generally CRT monitors were being used in your TVs and your monitors. But right now we are trying to use LCDs. LCD era is also being diminished right now. We are using LEDs right now. So LED TVs are being used generally in today's sense. So why also, as the name suggests, ray tubes. So basically these were sort of vacuum tubes only, which were being used for the implementation of visual colors, visual pictures in front of our eyes. But right now LCDs or LED TVs are generally being used for these purposes. So as you can see also CRT, the best example to understand the difference in the size of the tubes can be understood from these two examples only. If you have seen the CRT monitors are generally very bulky in size, sort of this nature. Let us say this is the tube. I am making a 2D shape, 2D space. Let us say this is your eye. So basically this is the visible screen, and these are the general sizes of your CRT monitors. And if you have seen today's LEDs, so LEDs are very thick, very thin. These are the LEDs which are being used today in day-to-day applications. So this is the view like this. So as you can see that this is the difference in sizes of CRT monitors and LCDs and LEDs. Okay, so this was one of the application, this was one of the usage. Much before the full implications of the semiconductor devices was formally understood, a naturally occurring crystal of galena. Galena, please remember what is galena. Galena is lead sulfide. With a metal point contact attached to it was used as a detector of radio waves. On the right hand side of the slide, you can see the this is nothing but your radio waves detector. Please remember, it is not used at the present moment, it was used dated back. So we will not go into details of how this radio wave detector was working. Just to make you a little quite familiar with whatever is written here, I just added the diagram of this radio wave detector. So just explaining it again. So much before the full implications of the semiconductor devices was formally understood, a naturally occurring crystal of galena or lead sulfide with a metal point contact attached to it was used as a detector of radio waves. Okay. In the following sections, we will we will introduce the basic concept of semiconductor physics and discuss some semiconductor devices like the junction diodes. We will understand what is junction diodes and what are bipolar junction transistor. So basically, a thing about transistor will be understood, a thing about diodes will be understood. We have already understood about resistors and current, electricity. You have already understood about capacitors and electrical charges and potential. So majority of the semiconductor electronics is already being known to you. Okay. So a few circuits illustrating their application will also be described. So ICs, logic gates, etc. will also be dealt in this complete lecture series. So it's a very big lecture series. Try to be very attentive. Try to be very try to not get confused with 2-3 things. Try to do revision every day. This thing will be much more clearer in that sense. Okay, so that was the end of your introduction part. So in introduction part, what was the basic crux we can get is, first of all, is that the discovery of vacuum tubes, in which vacuum tubes also called as valves, we also understood why were they called as valves. Okay, was being introduced, and then next came was solid state semiconductor devices. Okay, what was the basic difference between them? This is having low life, low reliability, working at high voltages, okay. What were the advantages of solid state semiconductor devices? High life, high reliability, and working at low voltages, working at low voltages. Okay, so this was the basic crux of what we understood in the previous discussion about introduction to this complete semiconductor electronics. One more thing is one of the examples which we understood, that was regarding CRT, that is cathode ray tubes, and next another was LCDs. Okay, so this is one of the application, and also we understood about one more example about this what was used as a detector of the radio waves. Okay, let's do the further discussion. So this is one of the typical example of, you can see the size of the electronic chips which are being used in today's date. So this can be understood as one of the small part of a motherboard, and this is one of the how a chip is being installed here. Okay, so you can see the sizes of chips, and you can you can observe it as comparing it with the this, what we can say, this vacuum tubes. The size is very small as compared to the vacuum tubes. Okay, so classification of metals, conductors and semiconductors. Let's start a second concept of this chapter about the classification of how the semiconductors can be classified as compared to their metals and your metals, or let's say conductors, insulators, etc. How are they different? Why is the name called as semiconductors? What is the difference between a conductor and a semiconductor, etc. will be dealt in this complete concept. Okay. So, on the basis of conductivity, let us first try to understand the difference between these things on the basis of conductivity. As the name suggests, please remember, you may have heard the concepts of conductivity in your chapter of current electricity also. So, basically what is conductivity? Conductivity is denoted by your symbol sigma. What is sigma? Sigma is nothing but your 1 upon rho. What is rho? Rho is basically your resistivity. Okay. For more concepts regarding this complete I guess one part of complete lecture was devoted on conductivity only, so you can go and just refer to those lectures. It is explained very clearly about this, the things, the concepts of resistivity is also been explained there, the things on which it is dependent upon, etc. is also been explained there, so you can just go and refer to those lectures also. Okay. So, on the basis of conductivity, on the basis of relative values of electrical conductivity or resistivity, it is also written here, resistivity is nothing but 1 upon sigma. The solids are broadly classified as, so basically there are 3 different types of classification. This is already known to us, the major contribution or the highest conductivity offering elements are called as metals, then come semiconductors and then comes insulators. As the name suggests, also semi, as in it is type partially conducting, partially not conducting, that is why the name is used as semiconductors, half. Okay. So, they possess very low resistivity or high conductivity. So, as you can say that rho value is approximately in the range of 10 to the power minus 2 to 10 to the power minus 8 ohm meter, and sigma, that is conductivity, is in the range of 10 to the power 2 to 10 to the power 8 s per meter. You do not need to remember these values can be just understood as a range, that what is the range of your metals, what is the range of your semiconductors, etc. Okay, next is semiconductors. Semiconductors have resistivity or conductivity intermediate as in between the metals and insulators. So, rho can be understood as between 10 to the power minus 5 to 10 to the power 6, and sigma can be understood as 10 to the power 2 10 to the power minus 6 as per meter. Going to insulators now. So, insulators have high resistivity. So, metals have low resistivity, insulators have high resistivity. Metals have high conductivity, insulators have low conductivity. They have the resistivity and conductivity in between those of metals and insulators. Okay. So, insulators, they have high resistivity and low conductivity. So, rho is directly is in the range of 10 to the power 11 to 10 to the power 19 ohm meter. Sigma is in the range of 10 to the power minus 11 to 10 to the power minus 19 s per meter. Okay. The values of rho and sigma given above are indicative of magnitude and could go well outside the ranges as well. So, this is just information part. Relative values of the resistivity are not the only criteria for distinguishing metals, insulators and semiconductors from each other. There are some other differences which will become clear as you go along with this chapter. So, this is not only the criteria on which we differentiate between metals, semiconductors and conductors, because let us say we are at the range of sigma in the range of 10 to the power 5. So, 10 to the power 5 is also in this range and 10 to the power is also in this range. So, how to differentiate between metals and semiconductors? So, that is why only this criteria can't be used for differentiation. Another criteria will be understood in subsequent slides. Okay. So, that is the end of this slide. Let us move to the next slide now. Okay. First, before moving on to the further discussions, let us try to understand what other type of semiconductors we are going to understand in this complete chapter. So, generally hearing you may have heard of elements such as silicon and germanium. Those are the major elements which we will understand in the complete lecture series of semiconductor electronics. What are silicon and germanium? Silicon and germanium are the examples of your semiconductors. Okay. So, let us go on what is written here. So, our interest in this chapter is the study of semiconductors, which could be, so now there are two types of semiconductors. First is the elemental semiconductors and second is the compound semiconductors. As the name suggests, majority of the things can be understood from the name itself. So, as the name suggests, elemental, as in semiconductors whose elements are directly being used. So, as elements are directly being used, we already know what are present in periodic table, elements are present. So, elements, so basically two examples of those elements are silicon and germanium. The denotation of silicon is Si and the denotation of germanium is Ge. Okay. Next comes compound in conductor. So basically compound as in a compound would have been made. So compound examples are, let's say, cadmium sulfide, then there is GaAs, gallium arsenide. So gallium arsenide was also being used in one of the lecture series previously conducted. So next is that CDSE, INP, iridium, phosphorus, etc. Okay. So these are one of the examples of elemental semiconductors and these are compound semiconductors. Majorly in this chapter we would be having discussion on your inorganic semiconductors only. So and silicon germanium also. So these are also can be explained under the inorganic part only. So examples are inorganic, that is cadmium sulfide, GaS, CDSE, INP, etc. Organic, anthracene, doped phthalocyanines, etc. Then organic polymers, polypyrrole, polyaniline, polyethylene, etc. Okay, so these are examples of your semiconductor devices only. So basically in one way or the another, these things are being used as a concept of why are they called semiconductors. One of the classification can be done on the basis of conductivity, that the conductivity of these compounds or these elements or these compounds are in the range of such that it is not even considered as a metal and cannot be considered as an insulator. Okay. Okay, next line is most of the current available semiconductor devices are based on elemental semiconductors, silicon or germanium, and compound inorganic semiconductors. So basically majority are silicon, germanium and this inorganic parts. Okay. However, after 1990, a few semiconductor devices using organic semiconductors and semiconducting polymers, so these are organic semiconductor and semiconducting polymers, have been developed, signaling the birth of a futuristic technology of polymer electronics and molecular electronics. So this is one of the new field of research which came into existence after 1990, which is called as polymer electronics and molecular electronics. Okay. In this chapter, we will restrict ourselves to the study of inorganic semiconductors, particularly elemental semiconductors, silicon and germanium. Okay. So in this chapter, we will restrict ourselves to the study of inorganic semiconductors, particularly elemental semiconductors, silicon and germanium. So as I already explained to you that we will understand only about majority of the topic is based on silicon and germanium only, but a little bit can be understood would be understood about inorganic semiconductors. Okay. The general concepts introduced here for discussing the elemental semiconductors by and large apply to the most of the compound semiconductors as well. So the concepts will be understood, we will understand about forward biasing, we will understand about reverse biasing, we will understand about transistors, N, P, etc. Majority of the concepts basically would be understood or can be, after those are being taught, they can be applied in organic semiconductors also. So the conclusion of this slide is just we just made understand that there are two types of semiconductors. One is elemental semiconductor, one are compound semiconductors. As the name suggests, elemental as in elements are being used there. Compound semiconductors as in some compounds are being used there. Compounds are divided into two parts. One is inorganic, one is organic. Majority of this lecture series will be based upon inorganic semiconductors and elemental semiconductors. Okay. Let's move on. Okay, so in the previous part we started with the concept of classification on the basis of conductivity, then we understood the types of semiconductors. Now we are trying to understand the classification on the basis of energy bands. You may ask that what are these energy bands. I will try to make you clear what is these energy bands being explained here. Okay, for now let me just iterate and then you will it will be much more clearer what is this energy band being talked about. So according to the Bohr atomic model, in an isolated atom, the energy of any of its electron is decided by the orbit in which it revolves. Okay. So Bohr's atomic model you may have heard, you may have studied in the initial phases of your chemistry. So I won't go into what is Bohr atomic model. So but you may have heard that the neutron and proton are residing in the center part, and then there are electrons residing in the circular orbits. Okay. So basically that thing is only written here. So according to the Bohr atomic model, in an isolated atom, let us say this is the isolated atom which I just made, let us say this is the isolated atom, the energy of any of its electron is decided by the orbit in which it revolves. So these concept has also been explained in the chemistry lectures only, I won't go into that. So I am just assuming that you know what is being explained here, that the energy is different for each of the electron which is residing in different orbits. Okay. But when the atoms come together to form a solid, they are close to each other, quite evident. So basically the atoms would come close to each other. So basically this complete type of orbits would have been something like this. So this can be one of the magnified view of some of the atoms. So the outer orbits of electrons from neighboring atoms would come very close or could even overlap. Okay, this would make the nature of electron motion in a solid very different from that in an isolated atom. So this was a major crux which I need to make you understand. This is the introduction part of energy bands. So basically what the crux is, that isolated atom will have the electrons moving in energy state, but as we try to make it or let us say we try to form a solid, then this all the orbits will come very close to each other, and sometime what would happen is that this nature of electron motion will be very different, and this will be very different from the isolated atom because they will come very close to each other. What will happen will be explained in the subsequent classes. Let me stop it here only. But the final point is that we need to understand that the nature of electron motion is different for the isolated atom and the solids in which it is very close to each other. Okay. So let me stop the discussion here only. So thank you so much.